Hello students, welcome to this class. Today we have this topic, types of organic reactions. An introduction. The most interesting and useful aspect of organic chemistry is the study of reactions and relevant synthetic applications. There are millions of reactions involving naturally occurring as well as synthetic organic molecules. It is very difficult to learn and understand each and every reaction if they are treated and analyzed as unique and isolated process. Using certain generalized basic principles, such vast organic reactions can be woven together and fitted neatly into general patterns. Based mainly on the functional groups, electron-rich sites, electron-deficient sites, and weak polar bonds of the molecules, organic reactions may be categorized into 4 general types. Number 1, substitution reaction. Number 2, addition reaction. Number 3, elimination reaction, and lastly the rearrangement reactions. In substitution reactions, an atom or group bonded to a carbon atom of the reactant molecule is replaced by a new atom or group. In addition reactions, 2 reactant molecules add together to form a single product. In the 4th rearrangement reactions, there is reorganization of bonds along with atoms and groups of the reactant molecule to give a new compound. Organic reactions. Enterprises in chemical synthesis concerned with the development of powerful and useful reactions, invention of strategies for the construction of defined target molecules. From static and dynamic aspects, organic reactions may be classified into 4 general categories. Number 1, substitution reactions. Number 2, addition reactions. Number 3, elimination reactions, and 4th, rearrangement reactions. Number 1, substitution reactions. Substitution reactions involve the replacement of an atom or group on the carbon atom of the reactant molecule by a new atom or group on the basis of the mechanism involved or nature of the substituted and the incoming atom or group. Substitution reactions may be classified into the following types. Number 1, nucleophilic substitution reactions. Number 2, electrophilic substitution reactions, and 3rd, free radical substitution reactions. Number 1, nucleophilic substitution reactions. In nucleophilic substitution reactions, both the attacking atom or group and the leaving atom or group are nucleophiles, that is, electron-rich species. These type of reactions occur mainly in compounds with an electronegative atom or group bonded to a sp3 hybridized carbon atom. For example, in the hydrolysis of bromomethane with aqueous sodium hydroxide to give methanol, the nucleophile hydroxide ion replaces the nucleophile bromide ion. Now, based on the timing of bond formation and bond cleavage at the carbon center, nucleophilic substitution at such sp3 hybridized carbon atom involves 2 main processes. Number 1, SN2 reaction. Number 2, SN1 reaction. First, SN2 reaction. Here, the abbreviation SN2 stands for substitution nucleophilic bimolecular. Now, this reaction, SN2 reaction, is characterized by number 1, a second order kinetics, number 2, a concerted single-step mechanism passing through a transition state without the intermediate species formation. And a third, stereospecific outcome, that is, different stereoisomers of the reactant gives different stereoisomers of the product. The backside attack of the incoming nucleophile turns the tetrahedral configuration around the carbon center inside out, and it is said to undergo inversion of configuration. This is often called Walden inversion. For example, in this reaction, S configuration of 2-bromobutane gives 2-butanol with R configuration at the chiral carbon. Now, SN1 reactions. The abbreviation SN1 here stands for substitution nucleophilic unimolecular, and these reactions are characterized by the observations. They are characterized by, number 1, a first order kinetics, number 2, a two-step mechanism in which the leaving group is released first in a reversible slow process generating a carbocation intermediate. This is followed by a fast second step in which the attacking nucleophile attaches to the carbocation intermediate, and they are non-stereospecific in nature, giving a mixture of inversion and retention in configuration around the reaction center. The attacking nucleophile can attach to the planar sp2 hybridized carbon atom from either side with equal chances. Nucleophilic substitution can take place at sp2 hybridized carbon of aromatic and acyl systems also. In these cases, however, the mechanism follows different processes. Aromatic nucleophilic substitution reactions. Now, in aromatic nucleophilic substitution reactions, the substitution takes place at aromatic carbon atom, and it goes in two different mechanisms. Number 1, elimination addition mechanism. This is also known as benzene mechanism. And number 2, addition elimination mechanism. Nucleophilic acyl substitution reactions. Now, substitution at acyl center takes place at the acyl carbon involving a general mechanism of two steps. In the first step, the attacking nucleophile adds to the reaction center, forming a tetrahedral intermediate, and this is followed by elimination of the leaving group. For example, propanol chloride on hydrolysis with alkali solution undergoes nucleophilic substitution at the acyl carbon atom. The second type of substitution reaction, electrophilic substitution reactions. Substitution reactions in which both the attacking group and the leaving group are electrophiles, that is, electron deficient species, are called electrophilic substitution reactions. Here, the leaving group is eliminated without the bonding electron pair, and the electron pair available is used to form a new sigma bond with the attacking electrophile. This type of substitution is generally encountered at aromatic ring with a hydrogen atom as the leaving group. For example, in nitration of benzene with a mixture of concentrated nitric acid and concentrated sulfur acid, the electrophile nitronium ion substitutes a proton from the aromatic ring. The mechanism processes through two basic steps. In the first step, generation of the electrophile and addition to the aromatic ring to produce a resonance stabilized sigma complex, also known as uranium ion, takes place. In the second step, the sigma complex regains the aromatic stability by eliminating a proton from the tetrahedral carbon atom. Free radical substitution. This type of reaction is not so common, but it is very important as it shows many effects in biological systems. A simple free radical substitution reaction may be cited by the chlorination of methane. In general, a free radical substitution reaction occurring at saturated sp3 hybridized carbon atom proceeds through a chain mechanism. The basic steps in the chain mechanism may be represented as chain initiation, chain propagation, and chain termination. In aromatic systems, however, the mechanism simply does not operate. In these systems, the reaction goes just like electrophilic substitution reactions. Now, the second type of organic reaction, that is addition reaction. In addition reaction, two molecules combine to form a product molecule. This type of reaction is generally encountered in substrate molecules containing multiple bonds. Based on the nature of the species added in the primary stage of the mechanism, the addition reaction may be electrophilic addition reaction, free radical addition reaction, and anionic or nucleophilic addition reaction. Now, number 1, electrophilic addition reaction. Here, in the first step of the reaction, the electrophile is added to the multiple bond and generates a carbocation intermediate. In the second stage of the reaction, a nucleophile adds to the cationic intermediate. For example, the addition of hydrogen bromide to ethene takes place by electrophilic addition mechanism. When the substrate and the reagent are unsymmetrical, the addition reaction shows resoselectivity. In such systems, the outcome of the addition reaction follows an empirical rule called Markovnikov's rule. According to the rule, the positive end of the reagent attaches to the multiple bonded carbon having more hydrogen atoms. Of all possible addition products, that one formed according to the rule will be the major product. For example, here the addition of hydrogen bromide to propane gives 2-bromopropane as the major product. Now, depending on the substrate and reaction conditions, the addition of the electrophile and the nucleophile shows electrochemical preferences. When they are added from the same side of the multiple bond, the addition is said to be syn addition, and addition from opposite sides is called anti-addition. For example, here the addition of bromine to butene is stereospecifically anti-addition. As a result, trans-butene specifically gives the mesoisomer of the product. Now, free radical addition reactions. Free radical addition reactions occur either in the gas phase or in an inert nonpolar solvent in the presence of ultraviolet light or diffuse sunlight, heat, or other radical sources like peroxides. The addition takes place here through the usual chain reaction steps: initiation, propagation, and termination. the addition of HBr to propene in the presence of a peroxide gives 1-bromopropane as a major product. Here, the addition is anti-Markovnikov in nature. Now, the third type of addition reaction, nucleophilic addition reaction. Nucleophilic addition reaction operates when electron withdrawing groups and atoms are present around the multiple bonds. For example, the addition of diethyl malonate to cyclohex to enone in the presence of a base takes place by the initial addition of the carbon ion formed by the removal of the acidic methylene hydrogen. Further, all addition reactions may take place not only at adjacent positions but also at 1,4 position. Now, the third type of organic reaction, elimination reaction. An elimination reaction involves the removal of 2 atoms or groups from the substrate molecule. Depending on the relative positions of the atoms from which the 2 atoms or groups are removed, elimination reactions may be classified into 2 main types. Number 1, alpha elimination, and number 2, beta elimination. In alpha elimination, also known as 1,1 elimination, the 2 atoms or groups are removed from the same center. Here, the reaction gives an unstable carbene or nitrene as product. The second type of reaction, beta elimination. Elimination reaction in which the 2 atoms or groups are removed from adjacent centers is called beta elimination or 1,2 elimination reaction. This type of elimination is the most common elimination reaction and results in the formation of a new pi bond. Depending on the conditions involved and timing of removal of the 2 atoms or groups, beta elimination reactions are classified into 3 types. Number 1, E1 reaction, number 2, E2 reaction, and number 3, E1CB reaction. Now, the first one, E1 reaction. Here, the abbreviation E1 stands for elimination unimolecular. The reaction obeys a first-order kinetics with the mechanism involving 2 basic steps. In the first slow rate determining step, the leaving group is eliminated along with the bonding electron pair to generate a carbocation intermediate. In the first second step, a base extracts a proton from the carbon atom adjacent to the cationic carbon, referred to as beta hydrogen, and a new pi bond is formed in between the 2 carbon atoms. E1 may be accompanied by rearrangement to give mixtures of products and is non-stereoscopic in nature. Now, the second type of beta elimination reaction, E2 reaction. Here, the abbreviation E2 stands for elimination bimolecular. It obeys a second-order kinetics and the mechanism takes place in a single step in which the 2 groups depart simultaneously with the proton being pulled up by a base. Stereochemically, E2 reaction is stereospecific in nature. The 2 atoms or groups may be trans to one another with a dihedral angle of 180 degree. This is called anti-periplanar, or they may be cis with a dihedral angle of 0 degree. This is called syn-periplanar. Elimination from anti-periplanar conformation is called anti-elimination, and elimination from the syn-periplanar conformation is called syn-elimination. Now, the third type of beta elimination reaction, E1CV reaction. E1CV stands for elimination unimolecular from conjugate base. The reaction mechanism goes in two steps. In the reversible first step, the beta hydrogen is removed by the base to generate a carbanion intermediate, that is conjugate base of the substrate. This second step involves the elimination of the leaving group as a new pi bond is formed using the electron pair of the anionic carbon. For example, the elimination of hydrogen bromide from 1-bromo to phenyl ethane to form styrene goes by this mechanism. This type of elimination reaction is most likely to take place with substrate having acidic beta hydrogen and 4 leaving groups. Now, irrespective of the types of mechanism involved, elimination reactions with substrates having 2 or more different beta hydrogen atoms, the multiple bond is formed regioselectively. The regioselectivity is governed by certain rules. Number 1, in the absence of specific conditions, the multiple bond is formed according to Jacob's rule. According to the rule, the elimination takes place to give the most substituted multiple bond, that is having least number of hydrogen atoms, will be the major product. In E2 reaction with charged leaving group like trialkyl ammonium and dialkyl sulfonium leaving groups, the elimination forms the least substituted multiple bond as predominant product if the substrate is acyclic. This is Hammond's rule. Now, the fourth type of organic reaction, rearrangement reaction. In rearrangement reactions, an atom or group migrates from the center to another center in the same molecule. The original center is called migration origin and the final center is called migration terminus. For example, the Hammond-Marcius rearrangement of an alkyl anilines to orthoalkyl and para-alkyl aniline. Now, the rearrangement reactions are classified into 3 main categories on the basis of the nature of the group transfer. Number 1, nucleophilic or anionic rearrangement. Number 2, electrophilic or cationic rearrangement. And the third, free radical rearrangement. Conclusion of the class. There are large numbers of organic compounds and reactions. It is almost not possible to learn and know all of them if we study them as isolated processes. It becomes easier when they are grouped together into some categories based on their kinetic and dynamic characters. These general groups are substitution, addition, elimination, and rearrangement reaction. Further, each group may be subdivided on the basis of the reactive intermediates involved or the nature of the reaction center. Different types of the reactions are accompanied by different stereochemical outcome also.